good morning, good evening, whatever time you are using or whatever time zone you are in. Um, I'm Timson, in case you're just watching this video. Today, last class we stopped at a point where we finished up with set, and I said something like we're gonna be entering into mutually exclusive. Next, we're gonna be talking about mutually exclusive set uh, in the next class, which we are going to start off with right now. Um, yes, mutually exclusive. What is the term mutually exclusive? What do they mean by a set being mutually exclusive? This is a very common term we're going to be coming across in our later exercises. And I feel obliged to let you know what it is so that when we start to get into it properly, we will not have any issues as to understanding what it actually is. So I'm going to be explaining what it is in a very quick way. So the term mutually exclusive refers to a condition or a relationship between, say, two or more events or possibilities. You understand? Where they cannot occur simultaneously. That is where two events or possibilities cannot occur simultaneously. So, in other words, if one event happens, it excludes the possibility of the other event happening at the same time. So, this is what it actually means. These events are said to be, say, mutually exclusive because they do not have any kind of overlap or intersection in their occurrence. So, that is what any event that doesn't have kind of overlapping or kind of intersection that's said to be in their occurrence rather are said to be what mutually exclusive. For example, let's say we have let's consider if, two cases here where you're flipping a coin and of course getting a head, you know, and of course let's say flipping a coin and getting a tail, those are two mutually exclusive situations. So another case, in this case of this scenario I just pictured out, you see that the events are mutually exclusive because it's not possible to get both heads and tail at the same time. You understand? And getting flipping a coin and getting um, a head and tail at the same time is something that is not possible. So you should know that these are what mutually exclusive scenario or event. So in probability theory, two events, let's say event A and B, are considered to be mutually exclusive if the probability of their intersection is zero, meaning that when you have a situation, say, let me write it out. Let me go. Sorry, excuse me. Let me write it out. So let's say we have a situation where we have a P of, let's say we have a P of A intersection B equals what? Equals zero. You understand? So that means the two events A and B, the two events here are A and B, and are considered to be mutually exclusive um, because the probability of their intersection is what is zero. Of course, this stands for intersection is zero. If you can remember in our previous lessons, so in some extent, you can consider the term mutually exclusive to refer to categories or options or groups that are distinct and separate. When you are saying something are very distinct or separate from each other, that is what it's typically mean by mutually exclusive. You understand? So when you have options or categories or groups that are distinct or separate, so that an item can belong to only one category and not to multiple category at the same times, then you can say what they are mutually exclusive. I hope I've been able to explain that. Or let me just quickly give a note on it so that let me just type out a note so that I can, let's say, this this set, these are sets which are which are allowed which are allowed which are not allowed, sorry, because they shouldn't be allowed, which are not allowed to have have any uh have any overlapping Yeah, have any kind of overlapping or intersection elements, section elements. You understand? So then it is also important to note that mutually exclusive, uh, mutually exclusive, mutually exclusive sets have set have um have the empty set as their intersection. Yes, have the empty set as their what intersection. You understand? So the intersection of two independent events or two events that are mutually exclusive is what is zero. You understand? Empty set. You understand? So therefore, we can simply say if the intersection of a number of sets is the empty set, then they are mutually exclusive and vice versa. Let me write it out. We can simply say uh, if the intersection of any numbers of sets numbers of sets, let's say no, is the if the intersection of any number of sets is the what empty set, empty set, then they are mutually what then they are mutually what exclusive and what say vice versa and vice versa. So that is that. That is if the intersection of any numbers of sets, say event A and B or set A and B is what empty, then of course you can consider those those sets to be what mutually exclusive. Just as we have in this case, in this picture that I put in. So the intersection of this and this is what empty set. Remember this sign is what intersection. So the intersection, if the intersection now equals to what zero or empty set, or you can say empty set. You can see in some cases where they have empty set, that is 0, 5. So empty set. You understand? It means what? They are what? Mutually exclusive. They are not having what? An overlapping element, or they are not intersecting. So if A and B are mutually exclusive, you can as well have a situation like this. Let's say if A and B are mutually exclusive, they can as well be saying A union B equals A plus B. Remember that in the last lesson, I told us that when you have a situation where the probability of A and B, set A and B equals zero, then it means that in the Venn diagram, this Venn diagram here, it means in the Venn diagram, this is A, this is B. You understand? This is A, this is B. There is no intersection between them. Here is empty. You understand? That means they are not overlapping. The two elements are not what overlapping. They are different from this scenario where you have this is a Venn diagram where you have set A and B. You see that these A and B, they are what intersecting. They are what overlapping. You understand? So definitely there is a common element between them here. So any element here what is a common element between what A and B. But here in this case, there's an emptiness. There's a space between them. There's no overlapping. So definitely to have a union of these two, you do what? You have to what? Add A and B together. And of course, it's because what? This is simply what? Intersection of A and B is what? Is empty, is zero. Nothing is intersecting them, nothing is overlapping. Then of course here the intersection, let's say the intersection here is what? C. So you see that the intersection of A and B here is what? Is C. So to now have union of this one, you now add what? A plus B minus what? The intersection. So here the intersection is what? Empty. You understand? So you just have what? A union B will now be what? A plus B. You understand? So in a situation where you have intersection, having have a situation where you have two elements not overlapping, that is not intersecting, then you can conclude that the intersection is zero, then you should have the A union B to be what? A plus B. So in this case, we can as well now say these two, this one is also what? Mutually exclusive, because A union B is what? A plus B. So whenever you see A union B to be A plus B, it means they have what? No common element, no intersection between them. So that is that about mutually exclusive. I hope you understand that. I hope you understand that. Then we are going to be moving to complement. Complement is just, it's not something I should repeat because we've talked about it. We've discussed about complement. You understand? We've discussed about complement. There's nothing we should talk again about. Let me just write out this first one. If if A U B equals A plus B, you understand? Then then again A and B are said to be mutually exclusive. Right? To be what? To be mutually exclusive. To be what? Mutually exclusive. So that is that about mutually exclusive uh, topic. Now we're going to be moving to complement. You know, I've said something about complement in our previous lessons, but I think curriculum wise, I should have just simply remind us of what it is. Then I move to independent and dependent event so that uh, we can forge ahead and we can, of course, be reminded of what we've been taught. So let me quickly run through what complement is. Remember, I said in the previous lessons, remember, I said complements are, remember, I said complements are values that are part of the sample space but not part of the set. You understand? Note that complements are always mutually exclusive. It's because I have to, you know, link it to mutual exclusiveness. So I just want to remind us. So you can see all values that are part of a sample space but not part of a set are what? Complement. They are part of the sample space, yes, but they are not part of a particular set. You understand? Then you can say they are what? Complement. What is sample space? Sample space is the total of all the uh all the values you have, or let's say all the elements you have. You understand? Then of course each sample space has what? Set, or let's say element. You understand? So that is that. So understand that complements are always mutually exclusive and not all mutually exclusive sets are what? Complements. So please let me write it out. Note that Let me write it out. Note that all complements are always mutually exclusive, and not all mutually mutually exclusive sets are what? Are uh, are complements. You understand? So this is simply saying that all complements, that is, all values in the sample space that are not in a particular set or that are not in the set are what? Mutually exclusive, are regarded to be what? Mutually exclusive. But not all mutually exclusive sets, you understand, are complements. Shall you understand? So let that not confuse you. So now we're gonna be moving towards independent and dependent event. Independent and what? Dependent event. Let me type that out. Independent and dependent events. Let me clean this off, please. Um, independent, independent, independent event. Independent and dependent what? Events. What are independent events? Let me start off with independent. Let me start off with independent event. Yes, independent independent events. What are independent events? Um, these are just all these terms. You might be wondering why I'm giving you all these terms. This is because they are necessary. They will be needed in your why we put for your in your later in your career or in your study. They will be far needed. So I believe it is important for me to just give them out, explain what they are, so that you won't get confused when the time for their need arise. So independent or dependent events are just simply times that are used to say describe the relationship between two or more events in the probability theory. You see, these terms can refer to how the occurrence of one event affect the likelihood of another event. You understand? So, what are independent events? Two events are considered to be independent if the occurrence of one event does not affect what the probability of the other event happening. You understand? So, in other words, the probability of one event occurring remains the same regardless of whether the other event occurs or not. For example, let's consider a situation whereby you are rolling a fair six-sided die twice. You know what the dice is. So you are rolling a fair six-sided dice twice. So the outcome of the first roll, e.g., say rolling a 4, does not impact the outcome of the second roll. So each roll is independent of the other, and of course, the probability of rolling any particular number, e.g., say rolling a 3 on the second roll, remains 1 over 6, of course, and just as it was for the first roll. So that is that. So in terms of probability, let me explain that in terms of probability. So in terms of probability, if A and B are independent events, then the probability of both events happening, that is A intersection B, is equal to the product of their what? Individual probability. Let me say we have something like this. Um let me say we have something like this. Let me clean this off. So remember the I said the term probability. In terms of probability, I said if A and B are independent events, then the probability of both events happening, let's say A intersection B, the probability of having A intersection B, you understand? Both happenings means A intersection B because they have what? Overlapping element is equal to the product of their individual probability. So you can now say, you can now say, uh, okay, this is what is equals to what? A times what? B. So in terms of probability, you can now say probability of both happening, that is A intersection B, of both happening equals what? The probability of A happening times the probability of what? B happening. You understand? The probability of what? B happening. So that is the meaning of what the definition I just gave. So then we have dependent event. You can say two sets are considered to be, let's say two sets are considered to be dependent if the occurrence of one event is just the opposite of independent event. So dependent event is, let's say two events are considered to be dependent if the occurrence of one event affects the probability of the other event happening. So the previous definition says one event occurring does not affect the probability of the other, but this one is saying um, a situation where the occurrence of one event affect the probability of the other event happening. So in this case, the outcome of the first event influences the likelihood of the second event. So for example, let's say okay, drawing cards rather from a deck without replacement is a classic example of what? Dependent event. So suppose you draw a card from a standard deck and of course you did not replace it, then the probability of drawing a card on the second draw is dependent on the outcome of the first draw because there is one less card in the deck after the first draw. Because when you drew a card, You didn't replace it. So not replacing it, the second draw will be affected because the deck is remaining, the number of deck remaining is that, okay, let's say out of 53 cards in a deck, for example, you now remove one. When you draw one, you have removed one, so you are left with 52. So if you want to run probability of the on the 52, it is what, less of one. So because you are not replacing it, so it will affect the um likelihood of the second event. So that is that about it. That's what I'm trying to say in essence. So in terms of probability, let's say if we say A and B are dependent event, then the probability of both happening is equals to the product of the probability of A occurring and the conditional probability of B occurring, given that A has already occurred. Remember, I told you something about that. You see that it's now coming out handy, is now coming handy, what we've thought before, what we've learned before. So the probability, this one is for uh independent event, independent. You understand? This is independent event. Yeah. Then the one I'm going to do now is dependent. So let me use red. Let me change the color. Let me use red. Hmm. Let me use red. Um, so let's say for dependent, let's say if A and B are dependent events, so A and what, and B are what, dependent events, then the probability of A and B happening is equal to the product of A and B occurring and the what, conditional probability of B occurring, given that A has already occurred. So invariably, if we can say PA intersection B equals what? PA intersection B equals probability of A probability of A times probability of what? B, given that A has what? Occurred. B, given that A has what? Occurred. You understand? Remember uh this one that we treated before in this particular aspect has been treated before. So this is the formula for probability of A and B, such of A and B if A and B are what, dependent events. So that is that about dependence and independence. So understanding this concept of dependence or independence event is very important. Please don't treat it with levity. They are important for calculating probabilities in various reward scenarios such as gambling, insurance, decision making process. So why you should not treat them with levity. You understand? Take them as something trivial. They are not trivial. Let me just write a simple note so that you can have it recorded. Let's say, uh, let me give a short note. Let's say this is a situation where the theoretical probability remains remains unaffected uh, by other events, remain unaffected by other events. Uh, as example can be example for example flipping a coin and getting a head and tail, and getting head and what, tail at the same time. So flipping a coin and what, getting head and tail at the same time. You understand? Just say flipping a coin and getting a head and tail. You understand? So it's not possible to get it at the same time. So they are what, independent event. So in the other case, we have what, dependent event. So dependent event is an event whose, let me write it out. It's an event. Just a short note to what I've explained before. It's an event whose probability varies as conditions change. And as what? Conditions change. As conditions change. For example, the probability of drawing a spade from the deck of cards. For example, the probability of drawing a spade from what? The probability of drawing a spade from the deck of card without replacements. Without replacement. Without what? Replacement. Then of course we have uh uh then that is that, and I gave example. Please make sure you are copying the note so that you won't have any need to revisit the video after. Always take down note. Then we are going to talk about conditional probability, and of course give some example on conditional probability. Then we move forward to um, of course reminding us of Bayes law, and of course move further to the let me quickly talk about those here. What are conditional probabilities? Conditional probabilities can be said to be the likelihood of an event occurring assuming a different one has already happened. Let me give an example. Let's say we have um, let's say we have let me first of all write what I just said. Conditional probabilities. Conditional probabilities. Conditional probabilities. I said it is the likelihood. The likelihood. It is the likelihood. Uh, say likelihood of an event. It is the likelihood of an event occurring if assuming, let's say assuming a different event has already occurred. You know, assuming a different event has already occurred or happened, say happened. So these are, so in a situation whereby you flip two coin, you can have probability of A to be probability of A given that B has occurred, which is what synonymous to what we have in the uh, dependent variable. So where we have uh, an independent situation. So if any two events are independent, remember I said it is what? P intersection B, say P intersection the two this thing where we have two P in intersection of the two events, where we have the multiplication of both of them happening. So remember that I said something about, let me bring out these. Let me clean this. So remember I said something about this. You understand? So which means it means probably to get this the value for this, you can say P of B, say when A has occurred, probability of B given that what A has occurred equals probability of um, say probability of B intersection A all over what? Probability of what? A. You understand? That is the meaning. That means if what? probability of A is greater than what? 0. So if you have probability of A given that B has occurred, just interchange what you have here. So it's the same thing. So I want you to know that this thing is not the same thing as this. You cannot say this is the same thing as this. Let's say probability of um probability of B given that A has occurred is not the same thing. It's not the same thing as, let me cancel the equals to. It's not the same thing as what? P of what? Uh uh A given that what? B has occurred. They are not the same thing. These and these are not equal to each other. So we have the law of total probability. Let's say okay, let me just give out the laws so that you will not get yourself confused. Let me give out the law. There's a law here. It says the law, one of the laws says, let me say inequality law. We can now say probability of A given that B has occurred is not the same thing as what? Probability of B given that A has what? Occurred. They are not the same thing. Then we have the this is the law of total probability. Then we have the additive rule. What is the additive rule? The additive rule says, let me just, I think it will be good if I type them out. Let me just type them out. Let's say the law of total probability. Let me use lowercase. The law of total probability. It says um, probability of A given that B has occurred is not the same thing as, I don't know how to strike, you know, it's not equal, is not equals to is not equals to probability of uh, probability of probability of B given A as what? Occur. So they are not equal. So that is the law of what? Total probability. Then we have the additive rule. You have the what? Additive rule. You have the what? Additive rule. What does the additive rule says? The additive rule says, uh remember in our previous lesson I said, in our previous classes I said something like, say, A union B equals, and I made mention of it earlier on, equals A plus B minus A intersection B. A intersection B. You understand? A intersection B. There's no intersection sign, so let me just type it. A what? Intersection B. Remember I said something like that, if you can remember. So the additive rule say the probability of union B will now be what? Probability of A plus probability of B equals what? Probability of, I mean, minus probability of B intersection, probability of A intersection B. Let me draw them out. Let me sketch them out. Remember I said that probability of A union B eh, equals probability of what? Uh, probability of A plus probability of what? B. You understand? Probability of A equals what? Plus probability of B. That is, A union B is what? A plus B. Remember. But remember that A union B means A intersection B complement. That is a situation where you don't have intersection. So let's say remember that a situation where A intersection B is 0. So now minus what? Probability of A intersection B. You understand? Now, remember that P intersection A intersection B is 0. So it will now be what? This minus 0, which is, remember, which is same thing as this. So don't forget that there's always this, but we didn't include it in the example I gave earlier because it amounted to what? 0. So in the case where you don't have 0, remember I said I drew a Venn diagram when they are overlapping. Let's say C is overlapping. It should have a probability of A, probability of B minus what? Probability of what? C. You understand? Then, of course, probability of A intersection B will now be what? Will now equals to what? Probability of A plus probability of B minus probability of A union what? B. Remember that too. So which is then that is about addictive. Then of course, multiplication rule is the rule of probability of A given that B has occurred that I give earlier on. So that is that. You can as well say probability of A intersection B is equals to what? Probability of B given that A has occurred multiplied by what? Probability of what? A. So don't forget that. Then I gave Bayes law. Bayes law is what? Probability of A given that B has occurred. That is the Bayes law. Remember I gave something like that. You understand? So probability of A given that what? B has occurred, which is what? Probability of A intersection B all over what? Um, probability of B. So therefore, you can as well say probability of A intersection B is same thing as probability of B given that, I mean, probability of A given that B has occurred is another thing as saying probability of B given that A has occurred multiplied by probability of A over probability of B, which is also what? Bayes theorem. So you understand? Where can we use Bayes theorems? What is the function of Bayes theorem? What is the real use case? It has the best use case in, say, medical research, you know, trying to find the causal relationship between symptoms. It helps us make more reasonable argument about uh, which one, which situation causes the other situation. So it has another use case, of course, in business and of course in various entity like that. So that is that. Then of course, we are going to be entering into probability distribution. You understand? We are going to be entering into what? Probability distribution. Let me Probability distribution. I think that should be um let me clean this off. Let me clean this off. So next this thing is now probability probability distribution. Distribution. You understand? So that is that about our next class. Please, um our next class is going to be done later today or max tomorrow. You understand? So I'll make sure I upload our next class today or tomorrow. So please stay tuned and wait for our next class. Thank you for your time and God bless. If you have any question, ask me in the comment section. I'll do my best to answer those, and you can feel free to share our video, click a like button, give us a good comment, subscribe to our channel, and write to me on Discord or Telegram or whatever you have my contact, please, if you have any issues. Thank you very much for your time and God bless.